Hello friends, welcome to my channel. Let's have a look at today's daily challenge problem. Problem 382, linked list random nodes. In this video, we're going to share a treatment based on sampling. So here, the two things we're going to use are random module in Python and the reservoir sampling method. First, I'll read through the problem statement to digest the requirement, and then we explain the reservoir sampling method. And finally, we share two formats of code depending on if the population size is known a priori or not. First, let's look at the problem statement. So given a singly linked list, return a random node's value from the linked list. So each node must have the same probability of being chosen. So here, actually, what we are required to do is to implement two methods in the solution class. So one is an initializer, and the other is the getRandom method. So here are one example. So in this example, this linked list has three nodes. So they have values 1, 2, 3. So we need to make sure these values are selected with equal probability. So the constraints for this problem are the following. First, the number of nodes in the linked list will be in the range given by the closed interval 1 and 10 to the power 4. And the node value is in this range, so this is not very essential. And thirdly, at most 10 to the power 4 calls will be made using this method. So this is the main statement. So now let's look at the treatment. So here we are going to use sampling. So here actually there's an assumption on the population. So if the population size is a priori unknown, so we just need to use the random zero choice method to select a random value. That will be enough. So otherwise, we could resort to reservoir sampling. So here a point to notice is that in the typically used algorithm R, for the replacement step, so a reset of element is required. For example, assume the reservoir size is k. In other words, we want to select k out of a certain population. Then when I when we look at the ith data points, so where I is larger than or equal to k, then we would like to do like this. We sample from the index, let's use one index from 1 up to I. Then we randomly pick one from this set. So let's see, this number we picked is g. So if g is less than or equal to k, right, in other words, in bound, so we're going to reset this jth element or index or element with index g with the current value in the population or the stream. Otherwise, we do not do reset. So in this problem here, we just need to select 1. So in other words, the reservoir size is 1. So in this case, so this reset step, so we can transform it to be a uniform sampling problem. So here we can do this. So we uniformly sample in the closed interval, right, 0, 1, and then a number f. Let's call the sampled number f. So if f is less than 1 over I, so I is the populations or the number of samples we have seen so far, then we are going to do reset. Otherwise, no reset. Then actually, this is similar, right? It's g less than or equal to k. The probability is k over I, right? So here k is 1. So the validity of reservoir sampling can be easily proved via mathematical induction. So actually we could check in particular the item here. So this is the algorithm R, right? So this is basically a very simple mathematical induction argument. So we're not going to explain here. So for interested audience, so you can check out this. So with that said, let's write the code. First, I'm going to assume that in the first solution, I'm going to assume population set is a priori known. Let's see, I'll call it n. So if this is the case, so actually we can, so here the population set will be the linked list length, right? So in this case, so we can store all the values of the nodes, and then we make it iterable or sequence, and then we just call the random choice method. So let's do this. So in this way of coding, so we put a lot of effort on the initialization method. So let's do this, self data. So let's initialize it as empty list, and then we're going to iterate over this linked list. So I'm going to set current equals height. Then we have a check while loop while current. What we're going to do is self data. So I'm going to append the current value to the data field. So it's current value. And then we are going to reset the current state. So in other words, each time when we do the when we instantiate an object or solution object, then we're going to populate this data field. So once we have this data field, then we can do this method. So because of the preparation in the initialization, it's very easy. So we just need to call random choice. So we're going to choose an element from this self data, so with equal probability. So that's the merit of this method. So before we look at the second method or algorithm R, let's first do a test. Yeah, it passes one example. Now let's look at the generic case. Yeah, it passes all the test cases. So with that said, I guess that's about it for the first format, in which we use the information about the population sets. So now let's copy this part, and then let's write another solution. So I'm going to change this one to be solution v1, and then we assume that the population set is not a priori known, or we can imagine this linked list representing a stream or something like this. So here what we are going to do is to use reservoir sampling, or let's choose a typical one, the algorithm R. So for this method, so our main effort will be in the getRandom method. For the initialization, it's much easier. So we just need to specify the height of this attribute or this field, and then let's do the reservoir sampling. So first, I'm going to call the samples sim to be 1. So here, I'm going to first set the value to be the height value. So in this case, so basically we use the constraint 1, because the number of nodes in the linked list will be in the range greater than or equal to 1. That's why the height is not null. So we can do self height value. This is valid due to assumption or constraint. Constraint item 1 or assumption, let's see. And then what we are going to do is to set the current to be self height. So rather than doing the things in the initialization, so we are going to do the while loop here. So while current. Then what we are going to do is to sample a random number. So because here we transformed the comparison of inbound sampling index to be a uniform sampling problem, we can just get a random number. Let's see, so the random. So let's use the uniform sampling. So this will be uniform between 0 and 1. I guess it's inclusive, right? So here, let's see, uniform. So this is inclusive. And then what we are going to do is to check the random number. If it's less than 1, this is the reservoir size. Here, the reservoir size is 1 over the current number of samples we have sim. So that is samples sim. right? So if this is the case, so we are going to do replacement. So we are going to reset the result to be current value. Otherwise, we do nothing. So once we do this, so we're going to modify the pointer, so or just update the current state. And then in this case, it means that we seen the current sample. So we're going to increment the sample seen by 1, right? So this is the main step for the reservoir sampling, or especially the algorithm R here. And then what we're going to return is nothing but the result state. So this is the second method for doing this problem. So before we do anything, let's first do a check. Yeah, here it passes one example. Now let's look at the generic case. Yeah, it passes all the cases. So notice that in the second solution, so the two things we need to pay attention to. First is that we actually transformed the index inbound sampling and the reset step to be a uniform sampling problem and probability check. This is one thing. And another thing is the initialization. So due to the assumption that the head is not null, so we first set the result to be the head value. So this is the second point. So with that said, I guess that's about it for this video. Thank you, and you're welcome to check out other videos in my channel for more problem analysis. That's it.